Greetings to everyone, and thanks for the invitation. It's nice to be back in Paris, even if on a screen. I would one day I will actually make it to the conference in person. It has so far never worked with my teaching schedule. I hope to get a sabbatical next year. So this talk is about a project that I have recently done with three coders: Tom Roby, Stephan Wagner, and Mei Yin. And this is all related to a question that was asked by Richard Stanley. I mean, a bunch of questions. It was a page full of questions, and I think we actually answered them all, which is a bit unexpected. You've all seen the abstract. Let me talk a little. So this talk has a bit of everything: algebra, combinatorics, a little bit of physics, which is clearly not my part, but we start with the algebra part, since I think this is probably the best known. So we're working, for most of this talk, we will be dealing with the field K of characteristic 0. And we're dealing with a free monoid with generators D and U, which I call M for monoid. So it just consists of words in D's and U's, purely combinatorial objects. W, on the other hand, is an algebraic object that is the Weyl algebra over the field K with generators D and U, and this famous Weyl algebra relation, du minus ud equals 1. So what is the purpose of the Weyl algebra? Well, obviously, it's there to formalize the connection between the derivative operator and the multiply by x operator. So there is a canonical representation of the Weyl algebra on the polynomial ring kx in a single variable, where dx is d over dx, and u acts as multiplied by x. And this is a faithful representation, so you can view this as actually the Weyl algebra being injected into the endomorphism ring of the polynomial ring. So what's the connection between M and W? Well, M is a free monoid, so you can map it to the multiplicative monoid of W, sending D and U to D and U respectively. This is, of course, not of course, but if you think about it for a while, you will see that this morphism is not injective, because W has a relation, du minus ud is 1. And well, this relation doesn't directly make du and ud the same in W. If you use it many times, you can sometimes get monomials that are equal. And one of the main questions of this talk is when exactly two monomials in D and U are equal in the Weyl algebra. Formally speaking, this is a question when two words U and V have the same image under phi, under this morphism from the free monoid to the Weyl algebra. And this is the first question that Richard Stanley asked. When are two words phi equivalent? Phi equivalent is just me calling it when the images under phi are the same. And we can ask this in different forms. We can ask for a combinatorial criterion. We can ask for an efficient algorithm that is called the word problem. We can ask for how many different phi equivalence classes of words are there if you, let's say, fix the length of the word, how large they are if they're finite. And we can ask what the minimal class of relations is that generates this phi equivalence. So if we want to define phi equivalence combinatorially by imposing a bunch of equivalences, what do we have to impose? Finally, we can ask what happens if the characteristic of K is not 0, or if we vary the algebra a bit, because the Weyl algebra is just the beginning of a family. So in this talk, we're going to answer the first three questions completely, and the last two to some extent. So there are still open questions around. In a way, there are many more open questions than there are solved questions right now, because there are so many algebras that are similar to this one. And I might sketch a bit of the proofs, but don't count on it. The whole thing is already on the archive, and it will be updated pretty soon with a little bit of details here and there. So I remind you that a word, let me say here that a word will mean just define a tuple of D's and U's. So M is a set of all words. We're going to use the standard notations from the theory of words. So a prefix, a suffix, or a factor A prefix is a subword that starts at the very beginning and is contiguous. A suffix is contiguous and ends at the end of the word. And a factor is contiguous but can be somewhere anywhere in the word. Words can be nicely encoded as paths because the letters D and U's, the names D and U are not chosen at random. You can view a U as an up step and a D as a down step. And by up and down, I mean northeast and southeast. So all my steps go one step right, but some of them also go above, and some also go down. So for example, here is a word UD, UU, DDD, and here is the corresponding path: U because up, D down, U so up, and down, down. Now this correspondence is almost a one-to-one correspondence, almost because you can freely choose where to start the path. I have started at the origin, but you don't have to. When you started at the origin, you call it the standard path of the word. Conversely, if you have a path and turn into a word by basically reading off its letters, so this is an up step, so you put it U, this is a down step, so you put it D, and so on, the word will be called the reading word and it will be denoted W of P. So in a way, these two constructions undo each other. Standard path, reading word, except of course you don't have to start at zero. A balanced word has equally many U's and D's. So in terms of the standard path, this means that it ends on the same horizontal line as where it begins. So for example, here it's not the case. Here you end one level deep, one level further down. Some more notations around paths. So a path for me is a tuple of vertices. This whole thing is, of course, a graph in a way, but for us, what it matters are just the vertices. The NE steps and the SE steps are encoded respectively as the vertices where the steps begin. So an NE step is a vertex for which the next step goes up. And southeast, so NE, of course, and SE stand for northeast and southeast. So a northeast step is a vertex from which you go northeast, and the southeast step is a vertex from which you go southeast. And I use this hopefully self-explanatory notation for northeast and southeast. So here is one nice thing you can do with words. You can, it's a bit like the Schützenberger involution. I call it omega. So what does it do? It takes a word, it reads it right to left, so it reverts it basically, and then it also changes every letter to the opposite. So D becomes U and U becomes D. And geometrically, it's even simpler. You take the lattice path and you just reflect it vertically, so left and right get swapped. This is formally speaking, this is an anti-automorphism of the free monoid M. And we can define basically the same anti-automorphism of the Weyl algebra, which sends D and U to U and D respectively, and also reverts the order of the factors. And I call them both omega because they nicely form a commutative diagram with a phi. Now, here are some subtler things that you can do with words. You can transform words into another words. So there are two ways to do this. And a balanced commutation means you find two consecutive factors that are both balanced, so x and y. So you write your word as some word p times some balanced word x times some balanced word y times another word q. We are not requiring that p and q are balanced. P and q can be arbitrary. It's the intermediate factors that must be balanced. And we swap those two balanced factors. So p, y, x, q is the result. That's called a balanced commutation because we commute two balanced factors. In a balanced flip, we pick just one balanced factor in somewhere in the word, and we apply omega to it. So this kind of vertical reflection, basically. So this is like the plexic monoid. So you can apply these operations in many places to a given word. They're not like deterministic transformations. They're like choices. So here is an example, and I'm showing you both the words and the corresponding diagonal paths so that you can see it maybe a little bit nicer on the picture. So what does a balanced commutation do? A balanced commutation finds a horizontal line that cuts the word that cuts the path at 3 points. I mean, it can cut it in more than 3 points, but you just pick 3 points where it cuts it. And then, so there is a left half and the right half. I mean, not literally half, but a left part and the right part between those cutting points. And so what a balanced commutation does, you're simply swapping those two parts. So the blue part and the yellow part get swapped. What a balanced flip does, I'm not doing anything with the yellow part here, but I'm reflecting the blue part across the vertical line. So, okay, I realize I should probably not have marked this part in yellow at the bottom. Okay, and on the word you see this here, but I think words are just harder to read than pictures. So the underlined and the overlined part are the factors that get swapped. So here are some more things you can do with words, specifically with the path. I should say that everything that you do for a path, you can do for a word because you just interpret the word as a path and apply the transformation to the path. So first of all, for any point, you call its y-coordinate its height for obvious reason. Now a path has an initial height and a final height, which are simply the height of the starting point and the height of the ending point. But we also care about the heights of the remaining points, and so we define 3 polynomials, specifically Laurent polynomials, because the heights can be negative, that basically serve as generating functions for those heights. The height polynomial basically takes the heights of all the points on the path, so all the ht of pi's, and puts them as exponents. So in a way, it encodes the multiset of the heights of the points by counting it. So if you have a point of height h, you get a z to the h element. Then there is the NE height polynomial, which is more selective. It takes only the heights of the northeast steps, of the up steps. And the SE height polynomial takes the heights of the SE steps, so the down steps. So for example, for the word UD, UUDDD, so this is the word with this path, the heights are seen in this picture. These are the northeast steps, these are the southeast steps. This is the last point, which is neither northeast nor southeast because it doesn't move. There is no way from it anywhere. And so the complete height polynomial encodes all the heights. So notice that there are 3 zeros. So the constant term is a 3. There is only 1 minus 1. So there is only 1 z to the minus 1, and so on. It's a Laurent polynomial, as you see here. But generally, its coefficients are just counting the number of points with a given height. And then there is NE height and SE height, where you only count the northeast steps or the southeast steps. One nice thing to notice right away is that neither of the polynomials changes if you apply a balanced commutation or a balanced flip. This is perhaps easiest to see on a picture, like here. When you swap those two pieces, the heights of the points don't change. All the changes is really where they lie, but if you take the multisets of the heights, they stay the same. And the same applies to a vertical reflection. It doesn't change the heights. So in a way, these height polynomials are invariants under balanced commutations and balanced flips. And this will be a crucial point in what follows. So now we state the main results. At this point, they are a bit overwhelming because of the number of different criterion. So maybe the main result is the equivalence theorem. It says that for any two words u and v, the following statements are equivalent. First of all, the words u and v are phi equivalent, so they have the same image in the Weyl algebra. Secondly, their images act the same way on the polynomial ring, where I remind you the action is d is differentiation and u is multiplication by x. The third statement is that the words have the same final height, so they end at the same height, or rather the respective standard paths end at the same height, and the same NE height polynomial. So in other words, the same multiset of heights of NE steps. Then I call the statement S3 prime for obvious reasons. The same statement, but with the SE heights instead of the NE heights. Then the same statement with the heights instead of the NE or SE heights. So basically, you can think of this as the same statement in three different versions. Then the word U can be transformed into V by balanced commutations. These are the operations where you swap two balanced factors. And finally, the word U can be transformed into V by balanced flips. This is the operation where you pick a balanced factor and you reflect it across the vertical axis. So all of these facts are equivalent. Finally, then there is a reflection theorem which says that every word is phi equivalent to its flip, basically. Sorry, okay, now I see that I made a mistake. Each balanced word is phi equivalent to its flip, to its omega. For non-balanced words, this cannot hold because the final heights will change. And in particular, as a consequence of the equivalence theorem, the word problem for this monoid, so the question of when two words are phi equivalents, can be solved in O of n time, so in linear time, basically, and also O of n memory. I mean, okay, this is not an immediate consequence, but it shouldn't be. It isn't too hard to see how to turn this into an algorithm that checks the phi equivalence. You would be using something like this. You shouldn't be using balanced commutations. You should use height polynomials for this. So, how could we prove this? Well, there are some parts that are easy. S1 implies S2, it's obvious because equal things act equally. S2 implies S1 is a well-known fact, which says that if two elements of the Weyl algebra act equally on the polynomial ring, they're equal. That's just the faithfulness of the Weyl algebra representation. Moreover, that the three height polynomials are invariants of balanced commutations and balanced flips shows that the last two statements, any of them, imply the previous three statements about height polynomials. The question is more like how you prove the other directions. So the non-trivial facts here are the other directions. At least one of the other directions is known, or more or less known. In fact, there is an observation by Diximier long ago that the Weyl algebra is z-graded if you give the u the degree 1 and the d degree -1. And then its zeros graded component is basically made of balanced words because you have to have the same number of u's and d's in the word. Strictly speaking, it is the span of the balanced words. And in fact, you can it's sufficient to take the span of the powers of the u. This is something that Diximier implicitly showed. But when you do that, it's just a polynomial ring in the u, so it's commutative. So in other words, any two balanced words commute in the Weyl algebra because they are in this zeros graded component, which is commutative. And so if you make a balanced commutation, in the Weyl algebra, you're swapping two commuting factors, so it will be the same element of the Weyl algebra. So there are some more things here that are in some form known, but not in the form that I'm using them. So there are still some things to prove here. The hard parts are still not obvious. So let me briefly mention how these things can be proved. I won't go into the details. There are some non-trivial results to be shown here, but I'll give you an outline. I define a word to be rising or falling depending on whether its standard path has more use than this or fewer use than this. Notice that I allow equality in both cases. So rising and falling overlap exactly in the balanced words. They are both rising and falling. I define a very specific type of falling word, which I call a downzig. It is a U followed by a bunch of Ds, followed again by a U. So notice that I require the bunch of Ds to be at least 2 Ds long, so I want it to be falling. And then I define a word to be abnormal if it is rising and contains no downzig as a factor. This is a weird condition. This is like a pattern avoidance condition, but I care only about factors, so only about contiguous patterns. So I want the word to be rising, and I want it to avoid all those patterns. So what can we see about those words? First of all, abnormal words have a very specific form. They are a bunch of Ds followed by a product of ud to the something times u, followed again by a bunch of Ds. And the bunches can be zero if they want to. Next, this follows easily from this characterization. An abnormal word is uniquely determined by its final height and its height polynomial. So it can be encoded just as a height polynomial. Note that the 3 height polynomials of a word can be transformed into each other. They can be converted, so they determine each other as long as you know the final height of the word. And this is in a way the key lemma. If a rising word is not abnormal, then you can find 2 consecutive balanced factors in it, such that the first one starts with a U and the second one starts with a D. So what can you do with them? Well, you can swap them using a balanced commutation. And because the first start with a U and the second start with a D, the result will be lexicographically smaller after the swap. And so this gives you a kind of straightening rule to rewrite rising words, making them smaller and smaller until they become abnormal using balanced commutations. And therefore, every rising word can be transformed by balanced commutations into an abnormal word. And moreover, using the first observations, you can show that this abnormal word is unique because the height polynomials don't change. This is a way to prove that that any 2 words with the same height polynomial can be transformed into each other using balanced commutations. At least when they're rising. If they're falling, you have to apply omega and then do the same trick. Actually, sorry, no, you don't have to apply omega. You have to apply a horizontal reflection. Sorry, I got slightly confused here. Wait, is this right? That's a vertical reflection. Anyway, horizontal definitely works. Maybe omega also works. Another of the implications requires us to show that anything that can be transformed by balanced commutations can also be transformed by balanced flips. And that is very direct. If you want to make a balanced commutation, you can also implement it in terms of 3 balanced flips. Namely, let's first flip P, let's then flip Q, and then let's then flip the product omega P, omega Q. And because omega is an anti-homomorphism, this ensures that Q and P end up in the opposite order. So all of this together yields the equivalence of the assertions, but, well, the last 5 assertions. S3, S3 prime, S4, S5, S6. Now, how can we connect this to the Weyl algebra? Well, when you look at how a given word acts on a given monomial in the polynomial ring, you can write this down explicitly. There is a direct formula for this action. Basically, the heights determine what happens to the degree of the monomial, but also the southeast steps being derivations and end up putting multiplicative factors in front of it. Because when you differentiate x to the k, you get k times x to the k minus 1. So all those k's end up as prefactors. Actually, you can. It's a little bit nicer to act on the Laurent polynomial rings, just because you don't have to deal with like negative. Sometimes the powers will go negative. And this formula tells you that if two words have the same action on each monomial, then those prefactors will be the same. And by applying this to arbitrary s, you can get some insight about the heights of the points on the path. And correspondingly, you get you can use this to show that if the actions of two words are the same on the Weyl algebra, then the height polynomials are the same. In fact, the heights are the same up to reordering. This connects the Weyl algebra statements with the remaining statements. So altogether, we have shown this equivalence theorem, which says that all of the 7 statements are equivalent. The phi images are the same, the phi images are equivalent to polynomials, the words have the same in E heights, the same as E heights, the same heights, they can be transformed by balanced commutations and by balanced flips. And the reflection theorem basically follows from it, because if a word is balanced, I forgot to say this, then it can be transformed into its omega by a balanced flip, but then the theorem says that this means that it's equivalent to its omega. So this answers the first couple questions. This answers the questions about when two words are phi equivalent in terms of combinatorial. This basically combinatorially describes it and gives an efficient algorithm for testing it. Now let's talk about counting equivalence classes. There are different ways to ask this question, but let's first ask the most natural form. Let's define A of n comma k to be the number of phi equivalence classes of words with k many down steps and n minus k many up steps. Some things are obvious. There is an obvious symmetry, which gives you A and k equals A and n minus k. Less obvious is a recursion. A and k is the sum as long as n is bigger than 2k. For n equals to 2k, you get an explicit formula, which is sort of nice. It is basically, well, a power of 2 times a linear factor. And then maybe less nice is a generating function. There are 2 versions of it, because of the symmetry, we can either have k go up to n over 2, or we can make it go up to n, but then we just get the same number twice. And I suspect that the first version is probably the nicer one, because the generating function is nicer. But a somewhat better answer from my point of view, is this formula here, the summation formula, which you can view as a combinatorial, as a re-expression of this generating function. So it's a sum of binomial coefficients times this factor. Now, as a bit of a curiosity, if you sum this over all k for a given n, you get the total number of phi equivalence classes of words of length n. And at least for positive n, so if you just tabulate it, you get a sequence which is weirdly not in the OAS. But it has a very explicit formula, if you don't mind a little bit of weirdness. So 2 times the Fibonacci number minus this strange-looking thing. So it depends on whether n is even or odd, which is perhaps not surprising, given that there is this kind of mismatch between even and odd here. And then there is this power of 2 times a linear term again. It's a pretty weird linear term. I like to say that this formula combines Fibonacci numbers and Catalan numbers. But really, this is a formula that you get when you just take this sum over k and simplify it in fairly standard ways. You can also get it from this recursion. So So much for the enumeration of all the words, or of the classes of all the words. But there is a variation where instead of considering all the words, you consider more or less something like dig words. Specifically, I'm going to look at the words whose every prefix has at least c times as many up steps as down steps. So these are words that whose paths go above a certain line, a certain line that starts at the origin and has slope c. And again, there is a recursion. And specifically, when the slope is a positive integer, there is an explicit formula, which weirdly enough, it's like combinatorial, but it has a minus here, which means you cannot really prove it bijectively. So it's a strange formula. But when C is 1 or 2, it becomes particularly nice. And those cases can even be proved bijectively. The general case requires the recursion. So the general case is an induction argument. Then we have a formula for the size of every equivalence class. Specifically, if you have a word with a given northeast height polynomial and southeast height polynomial, you can explicitly describe its equivalence, the size of its equivalence class, as a product of a bunch of binomial coefficients. There is a strange connection to something known in statistical physics as bond percolation. In a nutshell, bond percolation is a probabilistic model for percolation on a square grid. So you fix a number p, which will be the probability for something. You look at the integer lattice, but again, the steps you consider are northeast and southeast. So in particular, you only look at the lattice points where the coordinates have the same parity. The arcs are now called bonds, and every bond is open with probability p, and it's closed with probability 1 minus p. And now you look at, you drop some fluid at 0, 0, and you let it flow across every open bond to the right. So you imagine the plane to be tilted to the right. So the water flows downhill, but only if the bond is open. And the question is, which sides end up wet? So which sides or points end up getting some fluid? And in particular, people are answered in this infinite sum, where you look at for your sum over every side, the probability that the side has some fluid on it. This can be approximated as a power series on P. And you're looking at its coefficients, you realize that these coefficients look very much like those numbers. 1, 2, 4, 8, 15, 28. 1, 2, 4, 8, 15, 28. And these coefficients are in the OAS. And in fact, they agree with those numbers, but only up to n equals 11. After 11, they start diverging, and at some point, they even become negative. What's going on? Well, we don't really know. There is some similarity. There is a recursive way to compute these probabilities, which is called, what is it called? I call it dynamic programming, but it has a different name in physics. Anyway, if this recursion is somewhat similar to this recursion, and in a way, this bond percolation is like a probabilistic version of looking at just counting those words, but it's not clear what the exact relation is. There seems to be more to it. So this is a bit of an open-ended question. What exactly makes those coefficients equal up to n equals 11? Because coincidence up to 11 is not really a coincidence, apparently. At least it's weird. There is also a connection with something in combinatorics known as rook theory. In fact, this connection is pretty well known, but I'm not sure whether people have really studied it in full. Here is a quick reminder about rook theory. Rook theory is about you have a chessboard, but not like a complete chessboard. Only some cells are there. And specifically, in general, you can choose any subset of cells, but we will be looking at what is called Ferrer's boards, which are, in a sense, order ideals of a complete chessboard. Specifically, I can use a word of use and these as a way to describe a Ferrer's board. Namely, I take a right step for every U and an up step for every D. So I get a path. If my word is like this, then I go this U, D, D, U, D, U, U, D, U, D. So every U means a step to the right, every D means a step above. And then I fill in all the cells that are right and below this lattice path. This gives me a board. And now I'm thinking about all possible ways to put a rook on some cell. So I'm putting rooks on some cells of this board in such a way that the rooks don't attack each other. So no two rooks in the same row and no two rooks in the same column. This is called a rook placement in the board. So formally speaking, a rook placement is a subset of the board where no two cells have the same row or columns. And the rook numbers of the board, they count the ways to put k rooks that are not attacking. So the number of k element rook placements. Two boards are called rook equivalent if they share the same rook numbers. So rk of b equals rk of c for all k. And a very classical question that was studied back by Schützenberger and Fuata is when two Ferrer's boards are rook equivalent. But what has been studied a little bit later is actually rook placements are a combinatorial description for what happens if you take a monomial or a word in the Weyl algebra and you expand it in the basis of u to the id to the j. So if you keep applying this du equals ud plus 1 relation until there are no du's in the word anymore, until you transformed every du into ud plus 1, you get a linear combination of u powers times d powers, and the coefficients in this combination are precisely the k rook numbers of the corresponding Ferrer's board. And this allows you to extend the equivalence theorem a little bit by adding this extra statement, which is saying the boards are rook equivalent. However, there is a little catch. To make the statement equivalent to the previous 7 statements, you have to require that the words have the same number of u's and d's. So the same number of u's and the same number of d's. Otherwise, if you don't require this, the rook equivalence is weaker. Boards can be rook equivalent even if the words are not phi equivalent. And in fact, this is very easy to see because this board does not see the U at the beginning of the word. And it also does not see the D at the beginning of the word. If you remove them, the board will be the same because there is nothing below this U and there is nothing to the right of this D. So rook equivalence is basically phi equivalence, but as long as you also identify everything with the D, U at the front and the D at the end, you're allowing to put any number of U's at the front and any number of D's at the end, and you're ignoring them. So, but this means that rook theorists actually know some of this equivalence in this slightly weaker version where you can put U's and D's in the front and end. In particular, it's known among rook theorists that R1 implies S1. So rook equivalent boards give you the same monomials in the Weyl algebra. In some sense, rook theorists have also seen balanced flips in a weird form. It's called KK prime transform in this paper by Fuat and Schützenberger. But also, rook theory has been studied recently with a connection to finite fields. In fact, Haglund has noticed that rook polynomials count matrices over finite fields. This is a very fun connection. So it's best described by a picture again. If you have a Ferrer's board, you can view this as a mold for a matrix. So you put a matrix where in every cell of the board you can plug in an arbitrary element of a field, an arbitrary number. Whereas in the non-existing cells, you basically put zeros. So instead of filling the board with rooks, you're basically filling it with elements of a finite field, and you're completing it to a square matrix by putting zeros in the non-existing cells, so to make it a square. And then instead of asking yourself how many rook placements there are, you ask yourself how many matrices of this form there are, with non-zero entries only in the positions of the cells of the board, over a given finite field and of a given rank. And it turns out that those numbers are determined by the rook numbers. So in particular, two boards are rook equivalent even only if the corresponding numbers of matrices over every finite field of every given rank are equal. And in fact, as has been recently observed by Kotarto, Gruika, and Ravagnani just a year ago, you can even require this matrix rank equivalence for rank 1 only. You don't need to require it for all ranks. If it holds for rank 1, it holds for all the ranks. In a way, rook placements are like matrices over the field with one element, whatever this means. So this is like Q versions of rook placements. And nicely enough, we didn't have to prove these equivalences. They came for free from the paper by Kotarto, Gruika, and Travagnani. So let's answer question 4 a bit. As I said, the equivalence, so we described phi equivalence in terms of balanced commutations. But do we really need also balanced commutations, or can we do with a smaller set of commutations that are enough? Well, we can. I don't know what the smallest set is, or even if there is a smallest set, or there are several options, but one thing that you can do is, instead of requiring all balanced commutations, you require the irreducible balanced commutations, where you only commute two balanced factors if one of them begins with a u and the other begins with a d. So either x begins with u and y with d, or vice versa. And also they are irreducible, so they don't intersect the x-axis before their ending point. But let me move on to something more, I would say, more exciting. Namely, let's replace the Weyl algebra by other algebras. Because basically we can ask the same question for any algebra with generators and relations. One form in which we can ask it is we can simply replace the Weyl algebra by a multivariate Weyl algebra with many d's and many u's. And this is simply the algebra of differential operators on a polynomial ring in n variables. Well, the answer is a little bit boring. This multivariate Weyl algebra is simply the tensor product of n normal Weyl algebras. And correspondingly, every word in the multivariate Weyl algebra is just a tensor product of words in univariate Weyl algebras. And if you want to check when two words are equivalent, well, you have to check it factor by factor. So in every concrete I, they have to be equivalent. This is not obvious. It requires a bit of thinking, but it makes the criterion is obvious. The proof is maybe not. Then we can go to characteristic P from characteristic 0, where we have been working before. And that opens a whole new world. In fact, we don't know answers in characteristic P. We have some guesses as to what could get into those answers. Phi equivalence becomes less strict. So for example, you have those words which become, I call it P equivalent now because it's a different phi equivalence, which become equivalent in this Weyl algebra in characteristic P. And in fact, this is not surprising because u to the p and d to the p become central in characteristic P. This is a known fact. And the question is, what kind of commutation moves describe phi equivalence now? And the answer is we don't know. And also there are some quotients of the Weyl algebra that now appear. Previously, the Weyl algebra was simple. It did not have any proper ideals, so it did not have any quotients. But now in characteristic P, it gets those quotients, which are pretty meaningful. And you can ask this question about each of the quotients. You don't have to work with the whole Weyl algebra. So But there are also many algebras that are sort of deformed versions of, or generalized versions of the Weyl algebra. And one of them is called the down-up algebra. It's in fact, it's a whole family of algebras given by three parameters, alpha, beta, and gamma. It has two generators and two relations, which I admittedly look a bit weird. It takes some getting used to, but these relations encode a lot of interesting algebras. So these were found by Benkert and Roby. I think based on so this was originally meant to study quantum groups, but in particular you can get U of SL2 as one of the by setting the parameters to be this. You can get U of the Heisenberg-Weyl algebra, which is a homogeneous version of the Weyl algebra. And the Weyl algebra itself you can get as a quotient. And you can ask yourself when two monomials are become equivalent in the Weyl algebra, in the down-up algebra. And the answer is phi equivalence is always stronger than equivalence. The original phi equivalence in the Weyl algebra is at least as strong as phi equivalence in the down-up algebra. So whatever is phi equivalent in the Weyl algebra stays phi equivalent in the down-up algebra. But often the converse holds as well. And we don't quite know when it holds as well. We are not even sure whether there is a description. It feels like there is a bunch of sporadic cases and families maybe where you have extra equivalences creeping in. And as I said, you can ask this word problem in every algebra with generators and relations. I'm currently, due to another project, I am quite interested in Hecke algebras. So I'm wondering, in the Hecke algebra of the symmetric group, when are two words in the generators equivalent for generic Q? Is it equivalent to there being a braid? Is it the same as saying there are braid moves to turn one into the other? This might even be known. I don't know. I would love to hear an answer to this. Well, at this point, let me thank the organizers, let me thank my co-authors and Richard Stanley for the rather fruitful questions. And let me also thank Jürgen Beckelin, Gerard Duchamp, and Jill Brewster-Lewis for various conversations that in some way entered the above talk. Thank you.
Please, I'm speaker. Are there questions?
Maybe I have a little comment. First of all, little remark there. Yeah, you called Gerard Duchamp using French pronunciation. Maybe you should call Laurent polynomial, not Laurent polynomial.
Thank you. I'm not sure whether I got the Ravagnani correctly either.
Yeah, and what I want to say that accidentally, I thought about a couple of months ago, thinking about Gelfand-Kirill dimensions, which has a very weird definition. And I just try to make a little experiment. So you consider Weyl algebra and consider square field of fraction, which has because it has it's called Aura algebra. And you add X inverse and U inverse and D inverse. So it will be algebra with formula E and U inverse. And it turns out it has cubic growth. So if you consider filtration by number of generators, consider social gradient, then dimensions are 1, 4, 9, 16, 25 for social gradient. Yeah, so it's some bizarre fact. And
so quadratic, right?
Cubic because of the sum of squares. The dimension of
I see.
It's cubic, and in the way to understand it, it uses action on x to power s, but s should be not integer but indeterminate.
Yeah. That thing exists. That's quite useful if you're working a characteristic P, for example, but we have not used it in this work so far. Thank you.
Another question? Yes, Darij.
It seems to me that your work has some implications and relations to work of our student Wasiak about 20 years ago, who in his thesis considered generalizations of Stirling numbers which appear in taking powers of UD, and he, instead of taking powers of UD, he was taking powers of general words, of chain, if you and so on, and derived analytic formulas for such generalizations of Serling numbers, including generalizations of Bell numbers, which appear in the power in taking powers of words, more complicated than UD. And well, these are analytic formulas which are very pleasant. So maybe there is some deeper relation with your results.
So in a way, this is orthogonal. There is also this recent book by Mansour and Shork, I think, where maybe your student work has actually been is there, but we have not been like expanding specific powers of specific words. This is more of a general statement about when two words give the same expansion without computing the expansion.
I just mentioned that some of the results of Rorschach were summarized with Flageolet, with the article of Rorschach and Flageolet, which was the last work of Flageolet during his time.
Oh, okay, thanks. Good to know.
Yes,
We can send you.
We can send you. This is published in Séminaire Lotarangien.
Thank you.
Other questions, remarks, or comments? So, thank you, speaker.
Sorry, Darij. Can we ask a question online? Or
hi, Nicholas.
Hi.
Yeah, sure.
Thank you very much for the talk. I was so reminded by these pictures you had on these cuts on big path by something I, by pure accident, found from work of my collaborator Joachim Koch, because they have a construction called free decomposition spaces, which explains the construction of some combinatorial algebras. In particular, there was such an example where you, instead of having the ordinary algebra of dig path, you can get one where you have heights added in. I think it's possibly related to the kind of proofs you're doing from a combinatorial level. So maybe that would be an interesting paper to have a look at, because it feels like...
It's a remark by Nicolas Berry, if I hear well.
I would appreciate if you actually send me this paper, because I am looking for a good entrance point into the composition spaces that is as combinatorial as possible. I find the literature a little bit daunting.
Yes, because what you can do, there's a principled way of constructing a decomposition space starting from the free decomposition, starting from the decomposition space on just the dig path, and then having a left Kahn extension along the inclusion of this path, which just having the cuts on top and bottom part of a dig path. And then you get some new decomposition space, which in particular has grading by levels you put into the path. And it feels like some of your balanced operations might have a relationship. Maybe they fall into the grades of this decomposition. I'll send you a link. Yeah. Thanks a lot. Excellent talk.
Thank you.
So thanks last time. And the lunch is ready.
Enjoy.
Darij, can you stay online for a second? I just can drop you the link.
Yeah, why not? And I would also be happy to have a good example of Kahn extensions in combinatorics, where the notion actually makes sense.
Exactly this one.
I've been looking for this for a while.
The Baumann Foundation, and
I just put you the link, Darij. So it's a slide from my talk, and there's all the links to Joachim's papers that are relevant, and there's even a picture of this example with a free composition.
I will mention it.
So it's like a general construction which is relatively new. I think they published the preprint last year, maybe, I'm not sure, or 2 years ago. And it's a way of, so any decomposition space gives rise to incidence co-algebra and sometimes to bi-algebra, depending on the construction. But many of the examples which come of the concatenation type, they are examples of free construction. So basically there's a universal construction called free decomposition spaces, which arises from left Kahn extension along the inclusion of certain, you have this topologist delta, it's a category of simplices, and there's a subcategory of it, which are just the top and bottom face maps. If you know what, have you ever seen this or?
I don't know this one, also maybe I know it under a different name.
Yeah, possibly. But anyways, I sent the link to the slides in the chat,
Thank
and there
you.
you have all the references. Um, and yeah, but I mean, it's in particular this example of the dig path in the slides. It's like the last part before the tracelet stuff, and there you see this very beautiful construction of how you get a new. I mean, basically from a decomposition space, there's a natural way of extracting a co-algebra and also algebra sometimes. And in particular for the dig path, I found this. I mean, it immediately reminded me this way of putting cuts into dig path, but horizontally as an additional structure. And I wonder if this kind of new combinatorial structure has any link to your. It feels somehow you can basically cut your dig path into some pieces. You explained you had these special words in dig path which come back to the same height, right? Yeah,
I
in
mean,
the beginning
yes,
of it.
this definitely has this kind of cutting a path with a horizontal line
Yeah.
has a lot of relevance with our work.
So I imagine that might be a combinatorial way to
They record all the lectures. Yes. Oh, okay.
yeah. It's just a beautiful talk. Very interesting. And the other point, sorry, just not to hog all the time, but there's a way of there's a piece in this in the main paper I'm reviewing in this talk, the one by Joachim on decomposition spaces and combinatorics. There's a section on which kind of monoidal structures you can put compatibly with a decomposition space. And in particular, there's this point where they put these
It's
finite
only
vector fields.
not
And
online.
so I wonder if your example can be fully constructed in decomposition space here, the one where you start deforming the Heisenberg-Weyl by putting a different, what was it, a different field you had said also, finite field?
Yeah.
You come here every
Yeah.
time. I think.
So,
Okay, I think we're getting a lot of room noise right now.
yeah, sorry. Yeah. Anyways, just good to see you.
Okay.
And
Yeah, I won't understand it in a minute anyway. I'll have to take a proper look at it.
I just wanted to say Joachim will be giving 3 lectures here in Paris in May, because I'll send you a link when we know when it is. It's second half of May.
Yeah,
Yeah.
I'm afraid that May doesn't work for me just as much as this, like, unless they're also Zoom streamed.
That is on stream. Yeah. Yeah.
Okay, and I hope it's not too early in the morning to either.
But I mean, if you really want to see them and you can't attend, I'll record them for you. That's not a problem.
Okay. Anyways,
Wow.
thanks a lot.
This is a great connection. Thanks so much for bringing it out for us.
Ah, thanks. No, but it's just I so happen to work on with Joachim on something entirely unrelated, but I'm very interested in combinatorics. It's one of these crazy connections. I mean, Joachim basically, I'm an expert in rewriting theory, and I found a very, very elaborate construction of a Hopf algebra, which we needed for some purposes, and was a little bit unsatisfied because there was no immediate interpretation for why it should arise. And then I met Joachim at one of the combinatorics meeting organized by Gérard Duchamp, and suddenly he said, "Oh, this must be a decomposition space." And of course, I mean, who other than the people who, because Joachim co-invented them, so they were extremely new in 2019. So I mean, and then in 2021, we finally figured out how to do it, and it's such a beautiful story. And I mean, have a look at the slides if you want. It's just hallucinant kind of connection. But I mean, because we in particular then needed the free decomposition spaces, which were not even put in a preprint at the time, to finally get the link. And that's why, and now I really, we are writing a journal paper version of that, which is why I was very, very interested. And I put together some sort of review for this conference in the slides. And hopefully we'll give some intuitions and yeah.
Oh, this is great. I mean, this is what conferences are all about, is when we can make these unexpected connections. So thank you for taking the time to point it all out and to make sure we can find all the resources we need.
The main point being that as much as Joachim worked on the combinatorics, and he's very interested in combinatorics, I feel that especially the stick path example, there might be a lot of nice combinatorics in it because the way you get the beauty about this decomposition space is you get more or less without extra hand waving a lot of algebras out of it because and there's some degree of freedoms of, like in species theory, you can put different monoidal structures on top of species. And it's always sort of with the free decomposition spaces, you have all of these versions of deconcatenation type in it. And what they say already in this it's a small example in their paper, but they say it's funny because this algebra you get from the pre-decomposition space construction doesn't seem to be the one you typically would get for DigPath, the one with a word concatenation. So I thought
I have seen a bunch. I have seen a bunch of algebras on DigPath. I wouldn't even say that there is a canonical one.
No, exactly. But here, this is one which is combinatorially motivated and category theoretically, if you will. I mean, this decomposition space theory is relatively new, and the free version is like 2 years ago, or 3 years maybe. So it proved extremely useful for our purposes, but it seems to be something. I mean, it's a good organizational principle, I imagine, and I wouldn't be surprised if you find a version of it that fits your needs for. Just to give a combinatorial interpretation, the level of decomposition space would be fun. I mean, maybe useful. Who knows? Yeah.
Thanks a lot.
Thanks
so much.
Very entertaining talk. Also, thanks a lot. Yeah. See you soon. Unfortunately, I have to leave, but very nice to see you.
Yeah, see you soon.
Yeah.
Nice to meet you.
Nice to meet you too. Thanks.
Bye.